Greetings, Earthlings. Today we're going to look at Reinventing STUPID. Taking it from the lowly lab project it was to a new, enhanced, improved, updated, in some cases simplified, STUPID for the 21st century. So, as you recall, there were numerous limitations in the original design. And we'll review those here. And if you haven't seen the overview video, I talk about them in there, but we'll just go over them quickly in case you haven't seen that or you just need a little refresher. Okay. First and probably biggest thing to my mind was that there was a limited amount of RAM, only 256 bytes of memory, which is not enough to do much of anything useful. It makes for an okay demonstration, but if you actually wanted to try to do something with this, and I have no idea what that would be, you're going to need more memory. It had a limited instruction set, largely as a result of the limited amount of microprogram memory, which was also limited to 256, well, in this case, words. Oh no, the RAM, I'm sorry, let's go back. The RAM was 256 words, not bytes, 12-bit words. It had a limited set of registers, and as a result of that and some other issues, it was necessary to use memory for temporary storage in a couple of cases. So we'd like to eliminate that limitation. It had no carry bit or carry register, which meant you couldn't do overflow checking on operations, and you couldn't do multi-precision arithmetic with it. It had no TTY-in as a result of the restriction in the number of chips or selection of chips I was allowed to use. It was slow. It took multiple microcycles to read or write memory, and the microcode was held in a 1702 EEPROM, which had an access time of like 1 microsecond. And it had a hokey front panel because it didn't, it was not a custom front panel. And as a result of that and some of the other restrictions, it had this silly magic mode, which we'd like to get rid of. One other issue that I wouldn't call a limitation, but that complicated the design a little bit, was that due to the short length of the microcode instructions, there were 3 types of instructions. And so it required a little bit of jelly bean logic to do some decoding on that. Okay, so moving forward now, we'd like to have a full 4K of RAM, 12 bits of addressing. We'll have to figure out how to address that, since in the original design there were 4 bits of opcode and then 8 bits of address on most of the instructions. So that's going to require some indirect addressing. We'll get into that. And then we have the question of how to implement it. What technology? I decided to stay with 7400 series logic for the most part, not use programmable logic, except, of course, the microprogram memory is held in programmable. In this case, it will be flash memory, which gives me a much better access time than that old EEPROM. I have some AMD 2911s, old AMD 2911s, which I could have used, but they're not the A version of the parts, so they're pretty slow. So I decided not to use those. So it just uses a counter chip for the microprogram counter. Really, all you have to be able to do is increment or load the counter. The 2911 has some other features like a little stack and stuff, but we're not in need of that functionality in this design. And then there's the issue of how to actually implement it. Is it on a breadboard? Should I design a PC board or multiple PC boards for it? Should I do wire wrap? And so on. In this case, because it's a one-off thing, it doesn't really make sense to design a PC board. That would get quite expensive. I think I've had enough of wire wrap in my day. And the large number of chips kind of rules out the little plug board type implementation. So what I found is these Vector 4615 boards are called Euro cards, and I believe that I can fit it on 3 of these cards. One has the ALU and registers, another has the microcontroller, clock, and memory, and the third has the teletype interface and the front panel drive. Then there will be an actual printed circuit board for the front panel, which we'll get into later. Speaking of the front panel, I wanted to have a real custom front panel for this thing, and so here's what it's going to look like. As you see, it will display the program counter, the value of the accumulator, and the carry bit. That's way out there on the left. Memory address and memory data registers. There's a set of switches for entering data. These nested circles down here in the lower left, that's the power switch. It's a good old-fashioned key lock power switch, because that's what they did back in the day. And then there are momentary toggle switches, as you can see: reset, stop, load, step, start, continue, examine, examine next, and deposit next. So that's the front panel layout. I'm going to use LEDs for the indicators just because they're more efficient and they look cooler. Actually, look cooler and run cooler than incandescent lights. Now, there's a book called The Mythical Man Month by Fred Brooks, who worked at IBM. And one of the chapters in there is called The Second System Effect, which basically says that, people do an initial design and it's real simple and efficient and elegant, and then they get all these ideas for great things they can add. And then when they do the second system, they try to include all that functionality and all those great ideas into it, and it ends up being a big disaster, and it never meets its schedules, and it just drags on forever. So in order to avoid the second system effect, we're going to employ the KISS principle. Keep it stupid, stupid. Okay, and that means this is back up. This is an exercise in processor and instruction set design, okay? The object is not to build a full-blown computer system, okay? So it's not going to have interrupts, and it's not going to have anything other than teletype serial I/O. I'm not going to try and bodge a disk drive on there or anything like that. No DMA, nothing like that. Keep it stupid, stupid. However, I did potentially violate that in one case, at least one case. This is the one I'll admit to. Got my hands on some 74F670 chips, okay? These are 4x4 register files. And so because I want efficient memory-to-memory movement, I thought, I can have 4 indirect registers, and that will let you do memory moves quite efficiently, hopefully. So the microcode instructions will be 24 bits long in this new design, and that simplifies some things. There's really now only sort of 2 types of instructions. There's branches and there's everything else. And it won't take much in the way of decoding to tell the difference between the two. You really don't have to tell the difference between the two. What's going to happen is the ALU is going to operate in parallel with the Microinstructions sequencer, and you'll either load a new value into the microprogram counter or save the result of the ALU operation. So one of the jump options is no jump, and one of the destination options for the ALU is nowhere. Just throw it away. So the address, which would indicate where we want to branch to in microcode memory, overlaps the ALU operation, but that won't affect anything. I found some memory chips, 4K by 1 static RAM. These are CY2147s. 35 nanosecond access time. I like that. So 12 of those will give me 4K words of RAM, and we can do a read and a write in a single microcycle. Now, why these and not the 6116 type of chips, which are 6116 is 2K by 8. Is there a 6132? I don't know. But that might be 4K by 8. Take 2 of those and, call it done. Throw away 4 of the bits or use them for error correction or something. Error correction. You see, that would be violating the KISS principle. But the other thing is that these 2147s have a separate data in and data out line, whereas on those more modern chips, there's a single data bus. And for this stupid design, as it is designed, the separate input and output lines are more appropriate, work better. So that keeps it simple and stupid. What else? I'm going to allow up to 4K of microprogram memory. So there's 12 bits of the microcode can be used to specify an address, and the microprogram counter is 12 bits wide. That's probably way more than I'll ever need, so no more worries about that restriction. The carry bit, there's a flip-flop in there which will save the result of the carry out from the ALU, and that can then be tested and used. You can rotate through it as well. We've got some rotate and shift instructions that we didn't have before. Okay, so that's the plan going forward. We'll have another video coming up on the initial idea for the instruction set. Oh, it's changed. And then we'll talk about the microcode and actually look at the design as I start to put the thing together. So stay tuned.